after receiving. Also local first. After receiving. Calculate with your own local table. After the calculation, a new table is generated. The new table is then passed on to subsequent devices. This is a typical feature of RIP. Here is an algorithm for it. It is a very typical distance vector protocol. RIP is not easy to use though. But now there are also usage scenarios. It has long been unsuitable for the current network environment, because it has a limited number of hops. RIP up to 16 routers. Now there is almost no equipment inside. It is also necessary to specify the number of devices for the scene. Any medium or large network device. More than so many. So RIP is useless at all. This is what we call the distance vector protocol. A typical representative of it, called RIP. RIP as such a distance vector protocol. It will only update packages periodically by exchanging. To obtain network change information. It didn't trigger the update. It only has regular updates. Or take our example just now. In fact, I have drawn this picture many times over and over again. Two devices. There is a PC here. If the two devices run a RIP, there is a network segment here on the left. 1.0 segment. At some point this network segment disappeared. But since the device on the right now, just learn the network segment of 1.0 from the left. If this PC wants to access the 1.0 network segment, this device also needs to help it forward. Flow here. It still has to give this router. Because for RIP, it is not updated in real time. It will update every 30 seconds. So in the process, the device on the left still needs to continue sending data. So the first question is, it is definitely not possible to send data. Actually, this route makes no sense. So, this leads to the black hole problem we just mentioned. In this short time it will have a black hole. The second problem is a drainage problem. Drainage is, obviously, the device on the left does not have this network segment now. The 1.0 network segment is no longer here. Also direct the traffic of 1.0 to here. For this device, it drives a lot of traffic. The device still needs to process this message, because now it is going to the 1.0 network segment. Although the device will not process it looks up the table and cannot forward. Drop packets. I have to tear down the second floor first. Look at the second floor and look at the third floor. In the third layer, it is found that the data is going to the 1.0 network segment. And if there is no such data packet in its table, it will be discarded. Then the data will waste the forwarding performance of the device. That is, waste device hardware. It also wastes the bandwidth of this link. You may think, it's okay to waste some of this stuff. In fact, every beginner will have such an idea. But this is not okay for the network. As an agreement, this is a very serious common disease. This is absolutely not allowed to exist. Because it is a protocol. It is necessary to consider various optimization problems in the network. RIP optimizes every small link. Very poorly done. So this agreement is now gone. Of course, it is still configured on the device. But this thing is useless. Finally, let me briefly talk about horizontal split. I draw a picture to explain. Next time you see this word, it should also be the time to learn BGP in the NP phase. You will touch this split horizon again. I give a simple example. Now 3 devices, interconnected with each other. Assume that the RIP protocol is running in the middle. You don't need to have a deep understanding of this protocol. Now this has a network segment. 1.0 segment. Now device 1 wants to pass this network segment information to other devices. Suppose pass to device 2. And also to device 3. I mark it. This is device 1. This is device 2. This is device 3. This is 3 devices. Then device 1 now passes to device 2. Of course, after the local calculation of device 2 is completed, it will also be transmitted to device 3. Device 3 will also send it to device 1. After the local calculation is completed. This is how they pass. Device 1 will also pass its own information to device 3. This is RIP. An ancient mechanism. But it's not actually like that. I just give you a simple example. This information is passed back and forth like this. Then sometime. For the current device 1. This segment may no longer exist. This routing entry may be gone. But before it updates, maybe device 1 is receiving data packets from other devices. That is, it is possible that device 2 and device 3 have been sending data packets to device 1. Because the original device 2 learned the 1.0 network segment from device 1. It may be passed to device 3. Device 3 also gives device 1. At this time, device 1 will know. Because it now receives data from device 3. But device 3 receives it from device 2 here. Device 3 only knows that it will go to network segment 1.0 in the future. So it will find device 2. Device 1 also knows that it will find device 3 when going to network segment 1.0 in the future. Then for device 2. In the future, if you go to the 1.0 network segment, you will find device 1. Because that's what device 1 gave it. Since the information cannot be updated in real time, and the message is passed back and forth in the whole environment, it will just create a loop problem. Because the information is not updated in time. Then this problem is solved by splitting the horizon. Such an algorithm is very simple. It is the data sent from this interface will no longer receive from this interface. That is, as long as there is a data like 1.0 now, device 1 sends out to device 2 through this interface. Then it will no longer receive from this interface in the future. The data sent by device 1 to device 2 will not be received later. The data sent by device 1 to device 3 will not be retrieved in the future. That is, this routing entry sent by device 1, it will no longer receive. So that solves its problem. This is called split horizon. What we said above is several characteristics of distance vector routing protocols. Let's move on. Some defects of distance vector routing protocols. The first thing to mention is the trustworthiness of routing metrics. For a protocol like RIP, it takes into account its routing metric. Just think about one thing. Hop count. Each layer 3 interface passing through a router is called a hop. For example, there are 3 devices. There is a network segment here is 3.3. I now want to access from device 1 to 3.3. So that's 3 hops. Because the data ends up at this loopback port. This is also a hop count. It considers 3 hops. So now the whole is called cost. Or called metric. Going to 3.3 is 3 hops. But in this case, credibility is low. I draw a picture to explain